We have in the course of fluid mechanics discussed about viscous flows, and viscous flows are very important practical considerations in fluid mechanics, because we know that every fluid has a viscosity. So, viscous flows are practical representatives of the flows that are taking place all around. Now, on a different and idealized side of the paradigm, there is also another type of flow, which is the so called ideal fluid flow. So, what is that ideal type of fluid flow? That ideal type of fluid flow is first of all inviscid, that means it does not have any viscous effect. So, I want to iterate repeatedly that inviscid does not literally mean that viscosity of the fluid that is under consideration is 0. So, it may so happen that the fluid has a non-zero viscosity, but the rate of deformation itself is such that the shear stress, that is the product of the viscosity and the rate of deformation, that vanishes. So, inviscid flow will mean that there is no viscous effect, but let us say that there is a solid boundary on which a uniform velocity profile is coming, a fluid with uniform velocity profile is coming on the solid boundary. If that be the case, now this is clearly a depiction, at least this velocity profile snapshot is a depiction of zero shear stress. Why? Because the shear stress is the product of the viscosity times the velocity gradient. So, here there is no velocity gradient because it is uniform velocity, that means the shear stress is 0. So, to that extent it is this velocity profile snapshot is an inviscid flow. The bigger question is that given this velocity profile snapshot at the entry, can we treat the entire flow after the entry also as inviscid flow? This is a golden question, because often we do not answer that question. We see that it is inviscid flow and at some location, and then we try to make a speculation from that yes, we can treat the entire flow all the time at all places as inviscid one. Now, if you recall, one of the factors that we discussed which can make a flow which is inviscid here change its pattern. What is that? So, although this fluid velocity profile is uniform here, you have viscous effects playing a significant role in this entire part of the domain, whether it is the full part of the domain or a part of the domain which is close to the solid boundary. It depends on several factors, but there is viscous factor here. So, what a viscous factor tries to do is that this inviscid flow, it does not have a velocity gradient, and therefore it is also irrotational flow. This is the keyword which is of more importance to the topic that we are going to study now rather than the inviscid flow, because this is what we are banking on. So, we start with the uniform velocity profile. This uniform velocity profile is clearly irrotational, right. This uniform velocity profile, it is clearly irrotational, means what is irrotational and rotational flow? Let me just recapitulate if you have forgotten. So, the rotationality in a flow is described by the curl of the velocity vector, which is also called as vorticity. Okay. So, now if the, so this is a measure of strength of rotation in the flow. If this turns out to be a null vector, that shows that there is no rotationality in the flow, and we call that as irrotational flow. So, clearly this example is a uniform velocity profile, is a typical example where you may treat the flow as both inviscid and irrotational, right. Inviscid because there is no shear stress, but for our consideration in this particular chapter, it is also important to recognize that the curl of this uniform velocity profile is a null vector, that means it is irrotational flow. Question is again, it is inviscid here, it is irrotational here, can we treat this as inviscid here everywhere and irrotational here everywhere? So, clearly we cannot treat this as inviscid here everywhere, because of the effect of the solid boundary and the perturbation or disturbance in momentum created because of the presence of the solid boundary, there will be a propagation of this momentum disturbance of the solid boundary towards the outer fluid, and that propagation is through the fluid property viscosity. So, if the fluid itself does not have 0 viscosity, there will be viscous effect, no doubt about it. The viscous effects will be confined within a thin layer if the Reynolds number is large, otherwise the viscous effect will be penetrating deep. Let us assume for the time being that this flow is a high Reynolds number flow. So, if it is a high Reynolds number flow, the layer within which the viscous effect is important, of course this layer is not a horizontal line like this, but it grows like this. So, but outside this layer what happens is, so this is called as the boundary layer. So, within this boundary layer the viscous effect is important, outside the boundary layer the viscous effect is not important. That means outside the boundary layer you can treat the flow as inviscid flow. So, if you can treat the flow as inviscid flow, then whatever outer velocity profile which was irrotational will remain irrotational forever. So, the bottom line of our discussion is, if the flow is initially irrotational, it can be treated irrotational at other places provided viscous effects are absent, and of course other body forces are conservative. So, with this consideration we can say that inviscid plus irrotational, not just inviscid or not just irrotational, this is the deadly combination that we are looking for, because if it is irrotational at the, this irrotational means irrotational at the entry. So, if it is irrotational at the entry, it will remain irrotational at all other places where it is inviscid also. So, inviscid plus irrotational means it will be irrotational at all places. So, inviscid plus irrotational flow means that this is a null vector at all locations, and in that scenario you can, so if curl of a vector is a null vector, we can express this vector as the gradient of a scalar potential phi. This is based on the vector identity this is a vector identity, curl of grad of a scalar potential is a null vector. So that means we can say that these two are synonymous when the right hand side is 0. So this potential function is called as velocity potential, and flows where the velocity potential exists are called as potential flows. Now the question is that why do we study such an idealized paradigm? So this is very, very important. We will do very interesting mathematics over this chapter of potential flow which we are starting at this moment, but it is important to recognize that why it is so important, because immediately when we start discussing this, anybody will think that well, hardly there are situations when viscous effect is not important, right, all the practical flows are viscous flows. So is this just a mathematicians dream of doing good manipulations to find out the velocity potential for problems which are representatives of irrotational flows, or there is a practicality towards it? So let us try to answer this. So as I told you, in all high speed flows you have the flow region demarcated by the boundary layer which is adjacent to the solid boundary and a outer region which is outside the boundary layer. In the outer region the flow is inviscid and irrotational in this example, because an irrotational flow was already imposed on it. In the inside of the boundary layer, flow is definitely characterized by viscous effects. The common link that relates the outer flow with the inner flow is the pressure gradient. So there is a pressure gradient which is imposed on the fluid in the boundary layer, which is same as the pressure gradient which is imposed externally. This of course is detailed in the chapter of boundary layer theory. This is not within the purview of this chapter, but it is a very, very important consideration that the pressure gradient within the boundary layer which you require to solve the velocity in the boundary layer is same as the pressure gradient that is imposed in the outer flow, and the pressure gradient that is imposed in the outer flow can be obtained by looking into the solution of velocity in the outer flow which is a inviscid and irrotational flow. Therefore, analysis of inviscid and irrotational flow is required to get the velocity and pressure distribution outside the boundary layer, and that pressure distribution outside the boundary layer is imposed on the boundary layer to get the wall shear stress and so on. Therefore, although the fluid is not having zero viscosity, but an idealized paradigm of inviscid and irrotational flow outside the boundary layer actually helps you to solve the boundary layer equations, and that makes it a very practical proposition for doing fluid mechanics analysis. It is not a question of whether the fluid has zero viscosity or not, whether the flow everywhere is rotational or irrotational. See, within the boundary layer the flow is clearly rotational. So, you have to be careful about the use of inviscid and irrotational flow. It is not a question of whether all the domain can be treated as that, but even a part of the domain, if it can be treated as that, it helps in simplifying the governing equations considerably. So, with this background, we will start with this chapter of potential flow. This is essentially inviscid plus irrotational flow. So, by the name potential flow, it is quite clear that it is called as potential flow because velocity potential exists. So, for what kind of flow velocity potential exists? For irrotational flow the velocity potential exists. Now, what we will do is we will make another very important assumption. What is that assumption? That the flow is two dimensional and incompressible. So, consider this is in addition to inviscid and irrotational. Consider two dimensional and incompressible flow. So, the pure kinematic constraint of incompressibility of the flow will tell you that this is equal to 0, where u and v are the velocity components. So, you can write where psi, like the potential function phi, is another parametric function which is a function of x and y in this case. So, the way in which we define psi here is just to satisfy the incompressibility condition in a parametric form. Okay. So, when we write this psi is called as stream function. In our kinematics chapter we have already discussed that the stream function is constant along a streamline, but the difference between the concept of stream function and streamline is that streamline does not care whether it is two dimensional, incompressible, compressible, all these things. Streamlines are defined for all types of flow. Only for two dimensional and incompressible flow there is a connection between streamline and stream function, and that the connection is stream function is constant along a streamline. So, how do you know that? So, you recall that equation of streamline is dx by u equal to dy by v. I am not going to dz by w because it is a two dimensional flow. So, now psi is a function of x and y. So, d psi So, this is 0 along a streamline. That means why it is 0, because V dx is equal to U dy. So, these two terms cancel along a streamline. So, you can write from here also dy dx for psi equal to constant from the equation of the streamline, dy dx is V by U, right. So, these are the psi equal to constant lines. Similarly, you think of phi equal to constant, which are so called equipotential lines, and these are very important for potential flow. So, for a 2 dimensional, so now we consider a 2 dimensional and irrotational flow. So, irrotational flows are very general, they can be 3 dimensional also, but because we are bringing the stream function and velocity potential in the same platform, both we are considering as 2 dimensional flow. So, phi is a function of x and y. So, d phi so recall the definition. V is equal to grad phi. So, that means U is equal to so this is U dx plus V dy. So, phi equal to constant means d phi is equal to 0. So, dy dx will be minus U by V. So, dy dx for phi equal to constant times dy dx for psi equal to constant is this multiplied by this equal to minus 1, provided u and v are not 0. If u and v are 0, then there is a chance that you have division by 0 and the entire process of multiplication breaks down, and that singularity where u and v are 0, that singularity point is called a stagnation point. So, stagnation point is the point at which the velocities are 0, that means the fluid stagnates, so to say. So, we can infer from here that phi equal to constant and psi equal to constant lines are orthogonal to each other everywhere in the flow field except at the stagnation point. So, now because phi and psi are orthogonal to each other, we can define a complex function based on phi and psi. So, we will try to define that complex function now. So, let f be a complex number. We can write f see, just recall we write a complex number z as z equal to x plus iy. What is the basic premise on the basis of which we write it? X and y are in orthogonal direction, right. So, here phi and psi are in orthogonal direction, therefore, except the consideration at the stagnation point, we can define a complex function like this. What is the advantage? The advantage is that we are treating the velocity, potential and stream function together by a single complex variable. That is the advantage of doing this. So, and this phi and psi are functions of x and y. So, now we can write df dz. So, what is df dz? This is clear because it is a function of two variables x and y. So, how is z defined? So, df, so the first term, this is del phi del x plus I del psi del x, del x del z is 1 plus del f del y is del phi del y del y del z is 1 by I. 1 by I is as good as minus I, because I square is minus 1. Now, the question is that the function f, does it have a defined df dz? So, if it does not have a defined df dz, we say that it is not complex differentiable, or in another terminology we say it is not analytic. So, analytic and complex differentiable, these are two synonymous terms. So, is this complex derivative existing or not? So, we have to check this by noting that whether this derivative is independent of the direction in which the derivative is calculated. So, df dz along x equal to constant is what? Along x equal to constant, this will be 0. So, this will be minus I del phi del y plus del psi del y. Okay. And df dz along y equal to constant is, this derivatives of y will be 0. So, this part only. So, question is, are they equal or not? So, recall from our previous discussion, u is equal to del psi del y is equal to del phi del x. So, this was the definition of psi and phi through u and v. V is equal to minus del psi del x these are called as Cauchy-Riemann conditions. If these Cauchy-Riemann conditions are satisfied, and that is clearly satisfied for two dimensional incompressible and irrotational flow, what we can write here is that this is u, this is v, this is u, this is minus v. So, both are equal to u minus I v. That means that provided the Cauchy-Riemann conditions are satisfied, see up to this the mathematics does not understand what kind of flow it is, right. This is just rule of partial derivative, but the mathematics understands that eventually it is a 2-dimensional incompressible and irrotational flow through invoking the Cauchy-Riemann conditions, and then only the function f becomes analytic or complex differentiable. So, this implies that because the df dz is same along x equal to constant and y equal to constant, which are two representative directions and orthogonal directions, we can say that f is analytic or complex differentiable. Analytic or complex differentiable, that means the complex derivative in the complex plane exists. Okay. So, to sum it up, we have today discussed the importance of potential flow and we have introduced the way of defining a complex potential whose real part is the velocity potential and the imaginary part is the stream function. And in the subsequent discussions we will use this definition to bring out certain important characteristics of potential flow through defining first very simple types of flow and then linearly superimposing the simple flows to get more complex flows. Thank you very much.